1.8 we have doped semiconductor. So this is the crystal structure of n-type semiconductor, and this is p-type semiconductor. For n-type semiconductor, the bound charge is +1 because when the donor atom like phosphorus is added to the material, it donates an extra electron, and after losing this electron the donor atom becomes positively charged and there is an extra electron here. This positive charge are bound to the lattice, and the free electron can move into the lattice. And for p-type semiconductor, the acceptor atom takes one electron and becomes negatively charged, and there is a hole because it takes electron from here, and then this hole is the missing electron, and it acts like a positive charge carrier and it moves through the material. And this is why the bound charge for p-type semiconductor is +1 and for n-type is -1. And for this one I'm following the book Microelectronic Circuit. From the book I took the exercise 1.6 where they ask us to calculate the Ni, which is the number of free electrons and holes in the unit volume for intrinsic semiconductor, and then we have to find this Ni in the room temperature, which is 300 Kelvin. Previously we found the formula for finding Ni. So Ni is equal to Bt to the power 3/2 and e to the power negative Eg over 2 kT. And we know that B is the material dependent parameter, and B, the value of B is 7.3 into 10 to the power 15, and T is given to us, so it's 300 to the power 3/2. And we also know E is a constant, and the constant value for E is 2.718 to the power negative. Eg is the band gap energy, which is 1.12 electrovolt divided by 2 multiplied by the K, which is the Boltzmann constant, and it's 8.62 into 10 to the power -5 and multiplied by the temperature. I already calculated what's about value for this in my calculator, so I found that it's 1.5 into 10 to the power 10, and this is carrier per centimeter cube. And we know that the the electron concentration, which is Nn, is approximately equal to the Nd, which is the dopant concentration, and this is 10 to the power 17 carriers per centimeter cube. And the whole concentration Pn is approximately equal to Ni square divided by Nd. So Ni square is this, Ni is this one, and we square the value for Ni, and then we got this number, and then we divide it by the dopant concentration, and this gives us 2250, which we can express in scientific notation, which is 2.25 into 10 to the power 3 carriers per centimeter cube. And from here we can see that the whole concentration is less than the electron concentration, and the electron concentration is larger than the Ni. So we can write that the electron concentration is larger than Ni, and this is larger than the whole concentration. So majority carriers in the semiconductor are free electron. And that's why the value for concentration of the free electron is higher. So what we can also figure out what will happen if we increase the temperature. So there is another question which is you have to calculate the density, intrinsic carrier density of Ni for when the temperature is 350 Kelvin. So what we can do is we can use the previous formulas. N is approximately equal to the dopant concentration, that is 10 to the power 17 carriers per centimeter cube. And then we use the formula Pn approximately equal to Ni square divided by Nd, and Ni is something that we need to find when the temperature is 350 K. So we can use the formula Ni is equal to Bt to the power 3 over 2 e to the power negative Eg over 2 Kt. B is 7.3 into 10 to the power 15. Then temperature is 50 degree greater than the previous one, which is 350. So to the power 3 over 2, then multiplied by 2.718 to the power negative 1.12 electrovolt divided by 2 multiplied by Boltzmann's constant, which is 8.62 into 10 to the power negative 5 multiplied by the temperature 350. And I also calculated this in my calculator and found that its value is 4.16 into 10 to the power 11. And we can use this here, and then we can find the whole concentration from the equation. So we have Nd is 10 to the power 17, and if we use the calculator we can find it's 1.73 into 10 to the power 6 carrier per centimeter cube. So if we are increasing the temperature, we can see that the concentration of hole will increase 10,000 times, because this is 2.25 into 10 to the power 3 and this is 10 to the power 6. But still this is way more, the whole electron concentration is way more higher than the whole concentration. So after this we will go to chapter 1.9, which is current flow in the semiconductor. So there are two mechanisms when the current is flowing into the semiconductor. One is drift current, and we express this with the symbol Is, and another one is diffusion current. And we express the diffusion current with ID, and drift current happens because of electric field, and the diffusion current happens because of the concentration gradient. And to understand this, we will try to explain the mechanism using diagram. So let's assume that we have a voltage source, and this is applied across two plates. So this is the voltage source and these two are plate, and this is the length of the plate. And if we apply voltage to it, we will have an electric field here, and this electric field will be equal to the voltage, applied voltage divided by the length. And if there is a positive charge, it will flow this direction because this is negative, and if there is a negative charge, it will flow this direction because this is positive. So the direction of the positive charge is the same as the electric field, but the direction of the negative charge is the opposite of the electric field. And then we can also see that there are a lot of obstacles, and there are a lot of there are a lot of obstacles. Yeah, so that's why the velocity of this charge carrier are saturated. We can actually explain this using another diagram, so let's draw that. And then we can see if we apply voltage across it, there will be random flow of electrons charge. This is the electric field and this is the voltage. Because of the obstacles, the velocity of the charge carrier is saturated, meaning like when a charge carrier like electron moves through the material, they encounter obstacles and they are impurities or any defects, and these things slow them down and prevent their speed to reach the maximum level, which is known as the saturation velocity. And the drift current becomes steady and does not increase with more electric field or strength. And saturation means reaching a maximum level when where sometime like where something cannot increase anymore, like a sponge cannot hold any more water. So from here we can find the drift velocity for a p-type semiconductor is proportional to the electric field, and then we can introduce a constant which is mu p, and this is hole mobility, and multiply with electric field to get the velocity of the p-type semiconductor, the drift velocity. And the current is the movement of the charge carrier, so this movement is called drift current. And then for n-type semiconductor we will have similar thing, but the direction will be opposite, so it's negative electric field. And then the drift velocity for the n-type semiconductor is equal to mu n, which is the electron mobility, multiplied by the electric field. So from here we can calculate the current. The current for the p-type semiconductor will be area multiplied by the charge multiplied by the concentration of the hole, and then v drift velocity for the p-type semiconductor. So let's assume that we have like a box and we applied voltage across the box. So what will happen is the charge will flow with time, so I equal to del q over del t, and let's assume the cross-sectional area is length L, and the positive charge is flowing this direction. So the Q is 1.6 into 10 to the power minus 19 coulomb, and P is the hole concentration, and we know that rho V is the total number of holes. So total number of holes, and V is the volume. So if we multiply this number with the charge, we can get the total charge, which is Q rho V. And now what we can do is we can take the total charge, which is del Q equal to the total charge Q rho V, and we can substitute V, which is the cross-sectional area, with AL. A is the area and L is the length, so this becomes Q rho AL. And for the time, we know that the hole are passing, so the times of the holes are traveling L distance, so the time will be TL over P drift velocity, and then we can figure out the current, which is del Q over del T. Del Q is Q rho AL divided by AL P drift. This 2 cancels out, and then this goes up, and then we have the formula AQV p drift. And then we can also do the same thing for electron, which is the velocity of the n-type semiconductor. The drift velocity is equal to negative mu whole electron mobility multiplied by the electric field is equal to, so the current will be In equal to negative area Q and electron concentration, and the drift velocity of the electron. And if we take the area over here, we can get the current density. And for p-type semiconductor, the current density is Jp is equal to Q rho mu p whole mobility multiplied by electron. And for n-type semiconductor, we have Qn mu n e. And if we add these two together, we can get the total current density. And the total current density is just the summation of these two. So we can just write it down here. And this part is actually the conductivity, which is represented by sigma. And from here, so we can see that J equal to sigma electric field, and sigma is equal to Q concentration of the holes mu p whole mobility plus concentration of the electron multiplied by the electron mobility and multiplied by the electric field. And we know that Ohm's law says the electric current through a wire is directly related to the voltage, so I is equal to V, and it is inversely related to the resistance. So this Ohm's law's general form is J is equal to 1 over rho E. We can actually represent this simply by this equation, and we also know that the resistivity rho equal to 1 over sigma, which is 1 over Q p mu p plus n mu n. And we can just use another diagram to express this, like how it works, but it's the same idea. So we know I is equal to JA. J is the current density, and A is the cross-sectional area, and V is the electric field multiplied by the length, and R is rho L over M. So if we use these three formulas in our in I equal to V over R, we get JA is equal to E L over rho L over A. Then this cancels out, so J is equal to 1 over rho E. So from here we can use this for our math. And the mobility of electrons are actually 3 times larger than the holes, and we also know this from the number. So there is a number for mobility of the electron is 1350 centimeters square per VS, and the mobility of the holes is 480. And the free electron in the conduction band are loosely bound to the nucleus for n-type semiconductor, and for p-type semiconductor, the holes, which is the absence of electron, are more strongly bound to the nucleus. So that's why like the mobility of the electron is larger. And we can also express this using a diagram here. For example, if this is the conduction band and this is the valence band, so here we will have the positive charge and here we will have the negative charge, and then this is the energy gap, and this is the density of the state, and this is in terms of energy.